Hello, and welcome to this week's module. This week we're talking about the dynamics of the Pleistocene. And before we get into it, a couple of, I guess, just housekeeping things. We're sort of getting into the middle of the semester here. I know this semester is weird because we're not really doing a spring break and it's sort of just a different sort of schedule. I don't usually do midterms, so there's not going to be a midterm. I don't know if I don't think anyone's asked me about that, but just as a heads up, we're not going to do that. There will be a final, and I'll be sure to talk a lot more about that as we get closer to it. But we're sort of getting into the middle of the semester here, and just wanted to sort of check in and make sure everyone's doing okay. I know things are just a bit weird for this semester, so if you if you're having trouble getting things done on time or whatever, if you have questions about anything, you can always shoot me an email or a message on Canvas, and happy to talk through it, whatever you got going on. So. Um, Oh, and one other thing is that, so I know I'm probably behind, well, I'm definitely behind on grading. Usually, that's just kind of par for the course for me. I'm bad about staying on top of that, but I will work on getting that up to date over the next week, probably 2 weeks. Hopefully, we'll be up to date. So yeah, I'll be working on that. Okay, I think that's pretty much everything I wanted to go over. So yeah, if you have any questions about anything, just shoot me an email. So this week we're going to be talking about the dynamics of the Pleistocene. And last week we sort of went through the geologic changes and the geologic history of Earth, and it was we sort of went through all of it from like Pangea to where we are now, and that's pretty much the furthest back we're gonna go. It'd be tough to go much further back than that for the history of the Earth, but for the most part, this class that we're not really I don't take like a paleo sort of approach. So the Pleistocene is this epoch right before kind of where we're at right now, and I think it is worth going back and looking at the Pleistocene to sort of understand how things are right now, because that was sort of the most recent time period before where we're at. So there's sort of these direct lines that you can draw. So we're going to go back in time for the Pleistocene, but this is probably going to be the most backwards we end up going. So one thing that's really characteristic of this time period, that's the Pleistocene, and the specific time period is called an epoch. This is an epoch. But this time period is marked by these cycles of glacial and interglacial changes. So you have these patterns of the glaciers expanding and then retreating, and then expanding and retreating and expanding and retreating over and over again during this epoch, during the Pleistocene. And so we're going to take a look at what some of those drivers were, and what the biogeographic implications of that are. So let's sort of take a look at that. First, let's just sort of put this in context. So here we're looking at reconstructions of global air temperature and how they show the dynamic nature of the climate during the Pleistocene. And there's kind of a lot going on in this figure, so let's sort of break it down here. We're mostly, I mean, what we're talking about in this module is this time period right here, the Pleistocene. So we're sort of up here. This would be the present. If our x-axis is going backwards in time, this is the present here. And what you're looking at is air temperature. And it's sort of the different colors are the different periods, and we don't have to look at too much of that right now. Let's just focus on this period right here, which is basically this period here. And one other thing is this black line is basically the 1960 to 1990 average temperature. So looking at, how does that compare to somewhat similar temperatures that we have now? Obviously, our temperatures are warmer than that average now, but it gives you some current context. So that line is sort of a modern average. And if we're looking at the air temperature, which is just, this line, during the Pleistocene, what you can see is that, right around the start of the Pleistocene, it dips, like the sort of the average temperature, the overall temperature dips below where we're at now. And if you were to sort of draw a trend line through here, it's pretty much stays below there. Now, once we get into sort of the heart of the Pleistocene, you really start to see these spikes and dips in temperature in these cycles. And that's what I was talking about, that interglacier and glacier cycles. And what's going on here is the temperature is increasing, the average temperature is increasing and decreasing, increasing and decreasing. And that allows for, the expansion of glaciers and ice caps and polar ice, and then the retreat of it when it warms, and then the expansion. And so their ice volume is not on this figure, so it's not, you can't really visualize looking at this, but we're looking at temperature here, and you can obviously understand the implications of that. So when the temperature is high, this would be an interglacier period. Glaciers would retreat, and then when it dips, this is when glaciers would advance because the temperature drops. And then you have this period, which is the last glacial maximum. Basically, the last time the glaciers had the maximum extent that we've seen. And we'll come back to that in a little bit, but mostly I just wanted to put this in context because if you look over the past 500 million years, the temperature during the Pleistocene was probably the lowest it's been, other than this, the Permian glaciers here, which is like the snowball Earth sort of environment, which this figure is sort of pointing out here. This is the extent, this is the latitude, like how far in latitude did the glaciers extend during this time period, and this was the most. This was just a crazy time period, but we're talking about the Pleistocene here, and the main takeaway is that the temperature was lower. Average temperature was lower than it is now, and it was marked by these cycles of increasing and decreasing temperature. Okay, so let's talk about what some of the driving factors were, like what was causing these cycles of glaciation. And there was a number of them. So let's just sort of walk through these. First of all, there was variation in the amount of radiation emitted by the sun. So the sun, our star, goes through radiation cycles, which influences how much radiation it's emitting. I'm not going to go into that because that sort of gets into physics and astronomy and sort of beyond what the scope of this class is, but it's just something to be aware of. There's also variation in the absorptive and reflective nature of the atmosphere, and this is referred to as albedo, and I'll come back to albedo in a second. But basically, it's just how much radiation is being absorbed or reflected by the atmosphere that was changing. Similarly, there were differences in the albedo of Earth's surface, so how much radiation is Earth's surface absorbing and reflecting. We saw last week that there were lots of plate tectonic stuff going on. There's continents moving around and shifting and changing ocean currents, and ultimately these things can influence global climates on a pretty large scale. And also there's variation in the geometry of Earth's orbit, which is something else I'll come back to. And then finally, there's feedback interactions among all of these that can, one of these can influence the other and can influence the other. So there's all sorts of feedback interactions among these various drivers. I do want to mention albedo and give this a formal definition. So basically, albedo is just a proportion of solar radiation that is reflected by a surface. So if you have a lighter surface like snow or ice, that's going to reflect more sunlight, more radiation, and it's going to absorb less. So if you're near snow or ice, lots of snow or ice, the environment's probably going to be cooler than some other type of environment because it's reflecting a lot of that radiation. The opposite of that is if you're, on a really dark surface, and I think everyone's probably experienced that. If you've ever touched, asphalt or pavement during a hot summer day, it's really, really hot, and this, that contributes to like the urban heat island effect and things like that. So changes in albedo have a big impact on the distribution of energy and the pattern or trends of global climates. Oh yeah, I absolutely forgot I put this in here. I saw this on Twitter actually a couple days ago, and I wanted to show you. Since we're talking about albedo, this is a cool little thing. So I don't know where this photo was taken, but it's the surface of a lake, I think, frozen over. And so this is all ice, and there was an oak leaf that was sitting on the ice, and the oak leaf, has a darker surface than the surrounding ice does. So the oak leaf absorbed more solar radiation, and so what happened here is that the oak leaf heated up to a higher temperature than the ice did, and it just melted its way through the ice, leaving this perfect outline of an oak leaf here in the ice. So that's pretty cool. Pretty cool, interesting little example of albedo there. So I thought I'd include that. Okay, the other thing I wanted to sort of specifically mention here are these Milankovitch cycles, and these are this is the variation in the geometry of Earth's orbit is what I was referring to there. And there's a few different like features of this. I'm not going to go too much into this, but I think we should be aware of it because it was a contributing factor to this. So the first feature is eccentricity. And that's basically just a change in the shape of the orbit. And basically, what's the minimum distance to the sun, between the sun and the Earth, and what's the maximum, and how do those change? And it's measured as sort of a ratio. And so, if the difference between the maximum and minimum is low, then you're going to have more of a circular shape. If it's high, then you have this sort of off-center shape. Where there's a large difference between the minimum and the maximum, and it sort of oscillates between these two. So just and obviously that's going to impact how much direct solar radiation that the Earth is receiving. One of the other features is obliquity. So this is basically just a tilt of the orbit, pretty straightforward. What's that angle of tilt? And it sort of oscillates between a minimum tilt where we're at right now, which is sort of in the middle, and then a maximum tilt of 24.5. So, and that's going to change, obviously the angle changes how much radiation is reaching the surface per area. And then the last one is precession, and this is sort of the direction in which the Earth is tilted across its central axis, or away from its central axis, like which direction is it, and then that's going to influence sort of the wobble and the rotation around that central axis. So all of these together are going to influence how much solar radiation the Earth is receiving and where it's receiving that solar radiation, and sort of the density of the solar radiation per surface area. So those are things to keep in mind. If we wanted to sort of look at how these, it's kind of hard to visualize. So here we're seeing the Milankovitch cycles combined and how they influence solar insolation, which is the amount of radiation that Earth is receiving, and then the temperature that corresponds to that. And so you have the obliquity and eccentricity and precession here. And I think it's kind of hard to sort of like combine these in your head to figure out what would happen. But essentially what happens is like this figure down here. This is insolation. You can see, and this is over the last 2 million years, so most of the Pleistocene. You're seeing these sort of spikes and decreases and spikes and decreases. It's kind of hard to tell, but you can kind of see them in there as far as amount of radiation, but you can really see it in the temperature. So this is an oxygen isotope, and it's a proxy of air temperature. So we can just think of it as air temperature. You're seeing those spikes and decreases and spikes and decreases in temperature over these time periods. Okay, so that's what's going on with the climate and how it was driving that glaciation patterns. Let's take a look at the extent, like how much glaciation was actually occurring. So here, if we look during the Pleistocene, glacial ice cover extended down to temperate latitudes across the northern hemisphere, but it was less extensive in the southern hemisphere. Part of that's because there's just less land in the southern hemisphere. So let's look at the northern hemisphere, and it's kind of hard to orient yourself on these types of figures, but we're looking, straight. If we were like hovering above the Earth, looking straight down, this is the Arctic. And so this is North America and Europe and sort of the top half of Africa over here. So if that sort of orients you there. And what you're seeing here is this dark shading, which is this area in here and a little bit over here, is present day ice cover. The lighter shading, which is all the way down here around and around here and into Europe and stuff, that's the ice cover during the Pleistocene. And what you can see is it's way more extensive during the Pleistocene than what it is now. If we look it's kind of difficult to get a sense of where this is on North America, but this reached down to in Indiana and was way down here. So massive ice sheets covering large portions of North America during this time period, especially relative to what we have right now. And we can kind of, we can look at some other patterns, like with eccentricity and how that influences insulation and ultimately ice volume. There's a little bit of a lag. So, here's this decrease in eccentricity, and ice volume kind of follows that. You have this decrease in ice volume, and then it sort of increases, and you see an increase in ice volume, and then it decreases again, and you get a big decrease in ice volume. So you can see some of those trends. And this is basically just showing that eccentricity and how it relates to insulation and ultimately ice volume during the late Pleistocene. And so here you're seeing those interglacial periods. Ultimately, it's sort of decreasing, but you get these sort of periods because eccentricity is not the only thing changing at this time period. You get these oscillating periods of high ice volume and low ice volume over this time period. Okay, so I'm going to wrap up this video here, and there's a reading that's going to talk specifically about the last glacial maximum. So this is a specific period of time within the Pleistocene. It's not the full Pleistocene, it's just a small chunk of the Pleistocene. So take some time and read through that and keep working your way through the module, and I'll see you in the next video.